In the last video, we saw how to derive molecular geometries for electronic geometries that had 2, 3, and 4 electron clouds around the central atom. Now, 4 is the maximum number of clouds that you can have if your central atom is obeying the octet rule. But when your central atom has an expanded octet, you can have 5 or 6 clouds around the central atom. And we've already talked about the electronic geometries in a previous video for 5 electron clouds and 6 electron clouds. When you've got this situation where you've got an expanded octet on the central atom and 5 or 6 clouds, they call this hypervalent. So that's the name for molecular geometries, or that's the name for things that are derived from electronic geometries that have 5 or 6 or 7 clouds. 7 clouds can happen, but we're not going to worry about that. It's such a rare case. All right, let's look at molecular geometries that you can get from the trigonal bipyramidal shape. Let's remind ourselves of how the trigonal bipyramidal shape works. It's really 2 shapes superimposed. It's a linear shape that goes through the north pole and the south pole of the central atom. And it's a trigonal planar shape that goes around the equator. So we have axial and equatorial positions on this. And the bond angles are a bit different between different pairs of atoms. You've got a 90-degree angle between the axial positions and the equatorial positions. You've got a 120-degree angle between the equatorial positions. Now, this is going to matter to us when we do our molecular geometries. Why? Here's a little aside about electron clouds. Something that we haven't quite talked about yet. Some electron clouds need more room. In particular, bonding electrons between, say you've got this situation and you've got bonding electrons here. The electron cloud is tightly localized between the 2 atoms. The 2 atoms pin the cloud down, so it doesn't take up a lot of room. But if you've got lone pairs, they take up a lot of room. They're not pinned down on one end, so they can take up a lot of space. So these bonding pairs are taking up a very small amount of space, but the lone pairs need more. So some electron clouds need more room. In particular, lone pairs need more room. They'll take up more room. And when you put them onto your molecular geometry, you're going to see that they are going to crush the bond angle. Now, this is a tetrahedral electronic geometry in a water molecule. And in a tetrahedron, I would expect this bond angle to be the tetrahedral angle, 109.5 degrees. But the actual bond angle in water is 104 degrees. Why the difference? These lone pairs crush the bond angle so that they make it the angle a little bit smaller than what you would have otherwise expected. Now, if on a test someone asked you, what's the bond angle in water? And you said 109.5, I'd be pretty happy with that because you know the tetrahedral angle and you know that this is a tetrahedral electronic geometry. I'd be even happier though if you said, well, there's some lone pairs on here, so that will crush the bond angle slightly, and it should be something a little bit smaller than 109.5 degrees. You wouldn't have to say it was 104 degrees, but if you said it was a little bit smaller, that would be great. All right, with that in mind, let's ask ourselves, what is the roomiest position on a trigonal bipyramidal geometry? Unlike all the other geometries, this has two kinds of positions, the axial and the equatorial, and they're different. Well, if you look at the axial position, it's 90 degrees away from 3 atoms. And if you look at the equatorial position, it's 90 degrees away from only 2 positions. There are also two 120 degree interactions, but the 120 degree interactions are weaker. In other words, the equatorial positions are much less crowded, and you will always put lone pairs into the equatorial positions on this geometry. All right, let's go ahead and derive the molecular geometries. We are going to put an atom on each of these arms to get the first one. Here's the first one, and remember, when you don't have any lone pairs, you have got the same name for the molecular geometry as you had for the electronic geometry. Now let's put one lone pair on there. Now, we've got to put it in an equatorial position. How about if we put it there? Doesn't really matter which equatorial position we put the lone pair into. So there it is. Here are the axial positions, and here are the 2 remaining equatorial positions filled with atoms. Now, they call this a seesaw. And the reason is that if you tip this on its side, you could see that it looked a little bit like a seesaw with 2 legs, and here's the straight part of the seesaw. Sometimes people will call it a distorted tetrahedron, but that's a lot less common. Seesaw is usually what people call this. Now what if I put 2 lone pairs onto this? So I pull an arm off and put a lone pair in its place. I'm going to get something like this. I have to put that additional lone pair into the equatorial position. How about if we replace this one? Now, I'm going to call that a T-shape, because if you look at it from the side, you can see that it's a T-shape. There's like a 90-degree angle here, a 90-degree angle there, and it looks like a T. The final one, see if I can squeeze it in here, is going to have 3 lone pairs around the equator, and that is going to be linear, because if you look at the atoms, they're all down in a line. So that's a linear geometry. Now, these are the 4 molecular geometries that can go with a trigonal bipyramidal electronic geometry. Let's look at a few examples. Let's work out some molecules that have actually got these molecular geometries. Suppose I have got, we've already done SF4. So let's go back and look at the Lewis structure that we got for this. It's very similar to one you had on the worksheet last time. Here's the Lewis structure. I'm just drawing it in real quick without doing the step-by-step. The Lewis structure looked like this. There was 6 electrons or 3 lone pairs around each of the fluorines, and there's an extra lone pair that's thrown on the sulfur in the center. What would you say the electronic geometry is going to be for this? I would say, let's count how many clouds. A lone pair is a cloud. A bond is a cloud. There are 5 clouds, so it's got to be a trigonal bipyramidal electronic geometry. Okay, what about the molecular geometry? It's got to be a molecular geometry that is derived from trigonal bipyramidal electronic geometry. And it's got to have one lone pair. And if I have this table in my head, I can see that the only trigonal bipyramidal molecular geometry that has one lone pair is the seesaw. So the molecular geometry for this one is going to be seesaw. Let's do another one. Suppose I have the I3- ion, the triiodide ion. Let's do this one step by step. Step 1, you need a skeleton structure. How about if we put one eye in the center and all the other eyes on the outside? That'll work. Step 2, count the valence electrons. I've got 7 for each iodine. 7 and 7 and 7 is 21, and then one more for that electron. So I've got 22 valence electrons to work with. Step 3, connect the structure. That took away 4 electrons. I've got 18 left. The next step is satisfy the outside atoms. Okay, they want 8. They've already got 2, so I have to put 1, 2, 3, 4, 5, 6 on this one. 7, 8, 9, 10, 11, 12. 6 more on that one, which was 12 electrons, and I've got 6 left. The next step says take all your remaining electrons and pile them onto the central atom. And I group them as lone pairs. There are 3 lone pairs on there. That's 6 electrons. And that's my structure. Let's double check the formal charges on this thing. Okay, iodine has 7 valence electrons from the periodic table, and it's got 1, 2, 3, 4, 5, 6, 7 sticks and dots around it. So the formal charge on that iodine is 0. By symmetry, I can see that this iodine is the same setup, so I can very quickly write in its formal charge is 0 as well. How about this one? 7 on the periodic table minus 1, 2, 3, 4, 5, 6, 7, 8 sticks and dots around it. That's a -1. So I have to have a total -1 charge for all the formal charges, and I do. And 0, 0, -1 is about as good as I can get. So this is about the best Lewis structure I can draw for this thing. Now, let's ask ourselves, what's the electronic geometry? Okay, we got to count clouds around the central atom. When you're picking the electronic geometry, you're talking about the geometry around the central atom. You don't have to worry about the outside ones. Bonds or lone pairs are electron clouds. I got 3 lone pairs and 2 bonds, so that's a total of 5. And that means that this is a trigonal bipyramidal. Structure. It's got that electronic geometry. What's the molecular geometry? Well, it's got 3 lone pairs. It has to be a molecular geometry that's derived from trigonal bipyramidal with 3 lone pairs around the central atom. It's this one. This is the only one that has 3 lone pairs. It's the linear arrangement. So this is a linear electronic geometry, or I'm sorry, it's a linear molecular geometry, and it's a trigonal bipyramidal electronic geometry. Let's look at the octahedral case. Now you would think that there'd be a lot of these, but there aren't. There were only 3 molecular geometries that are common, that are derived from octahedral. The first one, we can just put an atom on every position. Now remember, the octahedral positions go like the x, y, and z axes. They go out at right angles to each other. and there are 6. So if I put something on there, if I put atoms on every arm right here, I'm going to get a molecular geometry that has got the same name as the electronic geometry. It's always that way when you have no lone pairs. This is an octahedral molecular geometry. Now when I put a lone pair on, I could put it on any one of these positions. I am going to choose to put it on the bottom position, just because that will show you a little bit more clearly why it's named what it's named. Now, this thing looks like a pyramid with a square base. There's a square, these 4 are in a flat square, and then this is pointing up on top of it, just like a pyramid. So they call this square pyramidal. And the final geometry is where we have a second lone pair on an octahedral. And I'm going to try to put that second lone pair. Remember, the lone pairs take up a lot of space. So I'm going to try and put it so that it's as far as possible from this first lone pair. If this was on the South Pole, I'm going to put the second lone pair on the North Pole. And here I've got a square planar molecular geometry. Now, this is a good final molecular geometry. This is the last of the molecular geometries that you need to know. In the very beginning, in the very first video, we talked about how the shape of a molecule was the basis for its biological recognition. Well, this shape, this square planar shape, led to a cancer drug that made a kind of cancer that was a major cause of death in the 20-year-old age group. It made it 99% curable. Here's how that shape works to cure cancer. A DNA molecule, you already know, carries your genetic information here, and it's a double helix. It's 2 strands that are sort of coiled together. And across those strands, they're held together by nucleotide base pairs. Now, think of these base pairs not as little lines like I've drawn them, but as like flat plates that have a seam in the middle. Now, when the DNA molecule unzips, these 2 flat plates can slide over each other and slide apart. The DNA molecule can unzip, and then a new plate can go, half plate can go on here, and a new half plate can go on here, and the DNA has replicated. So in order for the DNA to replicate, those 2 things have to be able to slide past each other. Now, when you've got that little square planar molecular geometry, it can fit in between those 2 plates like this. And it jams them together. So the 2 plates can't, the 2 strands of the DNA cannot slide apart because that's gumming up the works. It sticks in there and it prevents the 2 strands from zipping apart. And then the cell can't replicate, and it will eventually just die without leaving any descendants. Now, that's a bad thing in normal cellular activity. But in a cancer cell, in a tumor, where cells are rapidly dividing, you can halt the growth of the tumor with these square planar geometries. And this class of square planar geometry drugs are called cisplatins. And they have made certain kinds of reproductive organ cancers 99% and better curable. In the next video, we're going to talk about a consequence of molecular shapes, and that is polarity.